We are continuing on with section 6.8 here. Example 5 is graphing a cube root function. What is the graph of y equals 2 times the cube root of x plus 1 minus 4? We're going to start this off similarly to how we did the square root functions. We did quadratics, how we did absolute value, any of them that we've done so far by finding out our transformations. My 2 is going to be a stretch. My 1 means I'm going to go left 1 because it's a plus and it's inside that square root. It's left and right. I'm going to go minus 4, which means down 4. And keep in mind, all of this is based off a cubed root function. So to find my cube root parent function, I'm going to go from my table of values for my cubic function. And when we did a cubic function, we can plug in any x values that we want. And again, this is y equals x cubed. Negative 2, negative 1, 0, 1, and 2. Our domain on a cubic function is all real numbers. Here, I take negative 2 cubed, negative 8. Negative 1 cubed, negative 1. 0 cubed is 0. 1 cubed, 1, and 2 cubed, 8. Okay, now because we have the inverse function here as the cubed root instead of the cubed as in a power, we flop our x's and y's. So my parent function for a cubed root, okay, we just switch our x's and y's around. So x is negative 8, y is negative 2. Negative 1, negative 1. 0, 0, 1, 1, and 2. 8 and 2. Remember, we're swapping those. So my y's go to my x's go to my y's. And that gives me my parent function. So my parent function for the cubic here, the cubed root function, looks like this. And because it's a cubed root, and our cubic function is 1 to 1, that means its inverse is also a function. There's nothing I can't plug in to the cubed root of x. I'll always get a value, whether it's positive or negative, it doesn't matter. So here, that's one of the big differences versus like a square root that we did earlier in this section. With the square root, we only have the one branch. Here we have the entire function because with an odd root, we can have all of those values. Here, now I'm going to work with my translations. I'm going to take each point and I'm going to go left 1, down 4. Left 1, down 4. Or from like our vertex-y kind of point, I'm going to go over 1, up 1, over 1, down 1, over 8, up 2, over 8, down 2. Okay, and that's just these. I still need to do my stretch there. So my final thing I'm going to do here is instead of being up 1, I'm going to multiply that by 2 and go up 2. Here, instead of being 2 away from that middle vertex-y kind of point, I'm going to multiply it by 2 and go up 4. Instead of being down 1, I multiply by 2, down 2. And instead of being down 2 right now, I multiply by 2 and down 4. So my final function here is going to be the one in yellow. And it's going to look something kind of like this. Again, keep in mind, the curve itself is important, but what I'm going to really be looking at are your points. Because drawing these in is kind of rough. And again here, you don't need the parent function. That's my cubed root of x. And you don't need these purple spots. Again, those were just my horizontal and vertical translations. And then I included my stretch there. So keep in mind, instead of moving each point like that, we can go from our vertex type point here in the middle, over 1, up A, over 8, up 2 times A, back 1, down A, back 8, down 2 times our A value. Now, feel free to pause here and give this a try. I'm going to rewrite it just a little bit. This 3 in the front is just being added on to my root. So I'm going to move it to the end so that it's in a comparable form to what we normally have. Now, my negative is a reflection across the x. My half is a compression by a factor of a half. My 2, since it's x minus 2, that means it's just my 2 value, it's inside. I'm going to go right 2. And my 3 means I'm going to go up 3. Again, it's a positive 3 in the front, and we can put that wherever. So again, our parent function, and this is all based off a parent function of y equals the cubed root of x. So I have 0, 0, 1, 1, negative 1, negative 1, and then I have 8, 2, and negative 8, negative 2. And again, we get that because, oof, that was kind of rough. We get that because it is the inverse of y equals x cubed. And so our values there, we plug in negative 2, negative 1, 0, 1, and 2. Get our values, negative 8, negative 1, 0, 1, and 8. And then we flip our x's and our y's. You're going to want to try and draw a better line than I did through those points there. But at least we have the general idea of what it looks like. And keep in mind, because it's odd, we can have both sides. We can have every value there. Now, I'm going to go right 2 for every point and up 3. And that's going to be my new base point, like my vertex type thing here. I'm going to have to go reflection. So instead of going to the right and up, I'm going to go to the right and down. And usually here, it's 1 unit. But we're going to multiply that by my compression of a half. So I'm going to go right 1. Instead of going up, because it's reflected, I go down a half. And then usually I go over 8, up 2. But I'm going to multiply that by my compression. I'm going to go over 8 and down 1. Same thing in the other direction. Usually we go down 1. I multiply by a half. I go up a half. I go over 8. And instead of going down 2, I go up half of that distance, which is 1. So again, here instead of 2, it's half of that, which is 1. And because it's reflected, I'm going to go up. I can connect my dots here. And it looks something kind of like that. And I have my function. Again, reminder, that's based off the cubed root of x. We can graph any function of the form y equals a to the nth root of bx plus c plus k using transformations, as long as we can simplify the radicand and make the coefficient of x just 1. So this b value we somehow have to factor out so that our x value is just a 1. So here in example 6, I'm going to rewrite this graph using so that we can use transformations, and then I'm going to actually describe the graph, so tell what those transformations were. So here, the very first thing I'm going to try and do is I'm going to try and get rid of that 9. So I'm going to take a 9 out of 9 and out of 18. I'm going to factor out that common 9, and I'm left with x plus 2. Now I'm trying to take the square root of 9. 9 is 3 times 3. I'm looking for groups of 2. We don't have that 2 there, but we can put it. That group of 3 means it's going to come out of my radical. and I have 3 times the square root of x plus 2. And this is rewriting my function in a form that we can graph it using transformations. I took a 9 out of 9 and a 9 out of 18, and then I still had to take the square root of that 9, which gave me the 3 on the outside. Now to describe my graphs, I say what type of graph I start with. So here I'm going to start with the square root of x. That's my parent function. I'm going to stretch it vertically by a factor of 3. And I'm going to translate it left 2 because of what's inside my parentheses. So here, guys, once we get it into our form, we are just picking out our transformations like we did in the last example. Big thing though here is we have to also say what type of function we're starting with. Now, how can we rewrite our function here so that we can graph it using transformations and then describe the graph? Again, the big idea here is that we're trying to get the x with a coefficient of just 1. We don't want that 8 there in order to have it in our form that's easy to use transformations on. So here, I'm going to factor out the 8 from both pieces, and that's just inside my parentheses. So if I take an 8 out of 8x, I'm left with just an x. And if I take an 8 out of 32, I'm left with just a 4. Now, I'm trying to get the 8 out of my parentheses, or of my square root there, cubed root. So out of that cubed root, I can take a 4 times 2, which is 2 times 2. I'm looking for groups of 3. Here I have a group of 3 2's, so that comes outside of my radical. And I have y equals 2 times the cubed root of x plus 4. And again, I didn't change that minus 2 at all. So here is my function that I can use to get my transformations from. To describe my graph, I start off here with the cubed root function, the cubed root function. I'm going to stretch it vertically by a factor of 2 because of this guy. My plus 4 inside my cubed root means I'm going to translate left 4, and the minus 2 at the end means I'm also going to translate it down 2. So again here, make sure you let us know where you're starting. The idea here is that if we couldn't see the equation at all, we would still be able to graph it. So here we're going to start off with y equals the cubed root of x. We're going to stretch it by a factor of 2, translate it 4 to the left, and 2 units down. Recap here. A square root function is the inverse of a quadratic function that has a restricted domain. When we square each side of the equation, the resulting equation may have more solutions than the original equation. If f and its inverse are functions, and if either maps a to b, then the other maps b to a. And that's all I have here for section 6.8.